Hello, in this video, we are going to derive an expression for the natural lifetime tau of a reaction that is first order in the forward direction and first order in the second direction. Such a reaction is shown on the slide, A going to Z, with a rate constant K1 in the forward direction, K2 in the reverse direction. We can define a quantity D, which is the difference between the concentration of the product Z at any time and the concentration Z sub B, which would be the equilibrium concentration of Z. Also, let's define another quantity N, which is just the sum of the concentrations of the reactant A and the product Z. The rate of change of the concentration of the product with Z, dZ dt, is equal to K1 times the concentration of A minus K2 times the concentration of Z. And if we make our substitution that the concentration of A is equal to N minus the concentration of Z, then we get the expression that the change in concentration of Z is equal to K1 times the quantity N minus the concentration of Z minus K2 times the concentration of Z. Next, we form an expression for the change in the value big D per unit time. By using the rules of differentiation, we know that it has to be dz dt minus dze dt. Notice that since Z sub E, the equilibrium concentration of Z is a constant, that second differential is equal to 0, so therefore the change in D per unit time is exactly the same as the change in the concentration of Z per unit time. So therefore, dD dt is equal to K1 times the quantity N minus the concentration of Z minus K2 times the concentration of Z. Notice that at equilibrium, this change in D is going to be equal to 0, so long as the concentrations of Z are the equilibrium concentrations. So therefore, K1 times the quantity N minus Z sub N minus K2 times the concentration of Z sub N is equal to 0. In our next step, we're going to make use of the fact that if we add or subtract 0 from any quantity, we will not have changed it. So our new expression for dD dt is the previous expression from which we subtract that quantity that we saw in the last slide was equal to 0. And then when we do the algebraic recombinations, we get that dD dt is equal to K1 times the difference in concentration of Z between the equilibrium value and the current value minus K2 times the difference in the equilibrium concentration of Z minus the anytime concentration of Z. Next, we make use of the fact that the quantity in the parentheses, the equilibrium concentration of Z minus the current concentration of Z, is exactly equal to minus our quantity big D. So with making that substitution, the change in D per unit time is equal to minus the quantity K1 plus K2 times D. So this gives us a differential equation for dd dt that we can solve by the method of separation of variables. So as a first step, we get dd is equal to minus the quantity K1 plus K2 times D dt. So now we have expressions just involving big D on the left-hand side and expressions involving the other variable t on the right-hand side. And let us say that d has the value d sub 0 at the time t equals 0 as our initial value, our boundary value. So this gives us the natural log of d divided by d naught is equal to minus the quantity k1 plus k2 times t. And then if we multiply each side by minus 1 and use the properties of the logarithm, we get that the natural log of d0 divided by d is equal to the quantity k1 plus k2 times t. Next, we define a quantity tau, the natural lifetime, which is the time for d, the difference between the concentration of the product and its equilibrium concentration, to go 1 over e of the way from d naught to 0. So that means we're looking for when d sub 0 divided by d is equal to e. And if we take the logarithm of each side, that means when the log of d0 divided by d is equal to 1. Recall our solution for our differential equation, that the natural log of d sub 0 divided by d is equal to k1 plus k2 times t. And we realize that expression on the left-hand side is equal to 1 if we're looking for the natural lifetime. So therefore, we get that 1 is equal to the quantity k1 plus k2 times tau, the natural lifetime. And we simply divide each side by the quantity k1 plus k2 to get that the natural lifetime tau for this particular kinetic reaction is equal to 1 divided by k1 plus k2. I thank you very much for your kind attention. Stay healthy, stay safe, and as always, have a good one.